So we've talked about the first derivative and what the first derivative tells us about graphs of functions, and we've also talked about the second derivative and what the second derivative tells us about graphs of functions. So in this video, what we're going to focus on is basically putting it all together. The end goal is that we're going to get an accurate sketch of our graph, but I'll be honest, I really don't care a ton about sketching things. I care a little bit about sketching things. So we will actually have a nice sketch at the end, and I'll probably have you sketch some things maybe briefly from here on out, but I'm going to focus actually on how to just kind of put all the stuff that we've learned about the first and second derivative together and really analyze a function from start to finish. So we're going to do this in a couple of parts. We're going to analyze the original function, just f of x here. We're going to try and find information like what the domain of the function is, find any x-intercepts. If we've got y-intercepts that are easy to find, we can just throw those in there. Maybe we'll look for horizontal and vertical asymptotes. These are all things that we've done previously in algebra classes, and even with those asymptotes at the beginning of this class with infinite limits and limits at infinity. So since we've done this before, I'm going to focus less on this. We'll go through it to make sure that you know how to do everything, make sure that you know what's going on here, but we'll pretty much skim it, I guess. First derivative, though, this we're going to care more about. We're going to look for where a function is increasing and decreasing. We're going to find critical numbers, maximums, minimums, all that stuff. And with the second derivative, we're going to take a look at concavity, and we're going to try and find inflection points. So if we can get all of those pieces, then what we can do is plot all the interesting points, x-intercepts, maximums, minimums, inflection points, and then we can fill in the blanks with intervals where our function is increasing or decreasing, or maybe concave up and all that kind of stuff. So that's going to be the sketch at the end. That's supposed to be a period right here, not a comma. Oh, well. So that's what we're going to do. So I think the easiest way of doing this is to just go through an example. So we're going to start by analyzing the function. There's a couple of things that we want to look for here. We're going to be looking for the domain of our function. So this is the example that we're going to run through just to see how things work. I think this is a nice example to start with because it's not terrible to do everything, but it does have some interesting features. So we'll think about the domain of the function. The domain of the function, in this case, we'll notice that you can't put in 0. So some people will write it like this. Other people will just write this. I don't really care how to write it out specifically. That's not the real part that I'm interested in. The reason that I want to focus on the domain of our function right off the bat is because now I know that since 0 is not an x value in the domain of our function, I know that if that shows up as a partition number of the first derivative, it's not going to be a critical number. And in the second derivative even, if it looks like the concavity changes across that x value, it's not going to be an inflection point. So it's nice to get the domain part figured out so that you can check back to that at each other step to see what's going on. X-intercepts, here we're going to set our function equal to 0. So if we set 4x plus 3 over x squared equal to 0 and solve, we really only have to look at 4x plus 3 equals 0. And we're going to get negative 3/4. So maybe I'll write that here. X equals negative 3/4. There's my x-intercept. There's only one here. Sometimes you might have to factor and solve this kind of stuff. No big deal. For y-intercepts, we're going to set x equal to 0, and we'll look at f of 0. And we know that that's not going to be anything that we can do because we found out that the domain doesn't include this. You can see this really easily by looking at this and saying, oh no, it's 3 over 0. So for the y-intercepts, there's none. And we can see here why. This is a number over 0. There's a vertical asymptote here. So there's a vertical asymptote at x equals 0. That's why it's not included. And if we wanted to figure out the horizontal asymptote, what we need to do is look at a limit as x goes to infinity of 4x plus 3 over x squared. And if you remember, this is a long time ago, we can just look at the biggest terms. And so we're really looking at the limit as x goes to infinity of 4 over x, and that's going to go to 0. So we've got a horizontal asymptote at y equals 0. All right, that's a lot of stuff. What I'm going to say is that if you want to, go ahead and just graph your function on a graphing calculator. Be careful about how you plug it in. Make sure that you get parentheses around that whole numerator here. And you can find all of these features, really, from just looking at the graph. And I am absolutely okay with that. So go ahead and try and visualize things. At least make sure that it matches up with what you're finding. So when it comes down to it, these are some of the things that we'll try and refer back to when we plot our graph. We'll draw in the asymptotes, and we'll plot the x-intercept and all that kind of stuff. The main important thing for now, until we get to graphing stuff, is to recognize that when we deal with critical numbers and stuff like that, we do have this domain of x not being equal to 0. So any x values that are 0 are not going to be critical numbers, and they're not going to be inflection points or anything like that, even if they look like they might be. So that's how we would analyze the function itself. Now we'll move on to the first derivative. So we'll find the derivative, we're going to look for partition numbers, all that kind of stuff, do our regular analysis of that. So this is what it looks like. So we're going to find the partition numbers of f prime. We're going to check to make sure that they're critical. And again, we'll make sure that they're not 0. And then we'll go ahead and build up our little sign chart, because this was our domain, if you remember. So we're checking things across the domain. Then we'll build up our sign chart to figure out where it's increasing and decreasing, find all the local maximums and minimums, etc., etc., etc. What I want you to do is take a second, find the derivative. Excuse me. You can use whatever rules that you'd like. There are multiple ways of finding this first derivative. You might get a different looking answer than what I've got, but it'll essentially end up being the same thing. So pause the video and figure out what that first derivative is. All right, so this should be what we're looking at. You could do the quotient rule here. My guess is that a lot of people did that. Or if you wanted, you could notice that there's like an upside down triangle here. Or you could say this is 4x plus 3 times x to the negative 2 and do a product rule. Either way, you're going to end up with something like this as our derivative. So I went ahead and pulled out a little factor here. The reason that I did that is that it makes it a little bit easier to find partition numbers. Because now when we're looking for partition numbers, we've got two of them. We've got a partition number of 0. That's from our denominator. And we have a partition number of negative 3/2. Now, right off the bat, warning bells might be going off with this one. We know that the critical numbers are only going to be negative 3/2. Because 0, we said, for here, was a vertical asymptote. Oops, here we go. So we've got this critical number. Now what we need to do is set up our sign chart, and we'll figure out all of our intervals and all that kind of stuff and see what's going on. So I'm going to say our x values are going to go from negative infinity up to negative 3/2. Then from negative 3/2 up to 0. Notice 0 is still a partition number. We still are going to split up our sign chart around there because we want to see what's happening on either side of the asymptote. But what I might do here is put a little star to remind myself that this is not a critical number. Sometimes I'll go ahead and just write vertical asymptote to remind myself that if the first derivative test makes it look like this is a minimum or a maximum or something like that, I don't have to believe it because it's actually not a point. Okay, anyways, let's go ahead and see what happens for our derivative. If we go ahead and plug in some values for our derivative, maybe I'll pick something like negative 2. I end up with positive 8 minus 6. That's positive 2. So I have a positive number over negative 2 cubed is negative. Positive over a negative is negative. That means our function is going to start decreasing. After that, I can pick a number like maybe negative 1 in between these two things. And I'll throw negative 1 into that. That gives me positive 4 minus 6. That's a negative. Over negative 1 cubed. That's a negative. Negative over a negative is positive. So that means our function is going to be increasing. Since this is a critical number, And if you wanted, you could remember that that's because the derivative was equal to 0 in the middle. That's helpful because now we know graphically that's going to be a horizontal tangent line and not a sharp corner. But since it's a critical point, we can say the first derivative test tells us that this is going to be a minimum at that x value. Over here at 0, we're going to maybe put like a little vertical asymptote here. You can use whatever symbol you want to remind yourself what's going on with the derivative. But now if you plug in a number that's positive, like let's plug in 1 here, we get -4 minus 6. That's going to be really negative. That's -10 over 1 cubed. So negative over positive, that's negative. That means our function is going to decrease. So it's going to increase on negative infinity to -3/2, and, sorry, that's wrong. It's going to decrease on that interval. So it's going to increase on -3/2 to 0, and it's going to decrease on negative infinity to -3/2 and 0 up to infinity. And we have a local min at x equals, -3/2. There we go. We'll find the y value later when we go plot it. But that's everything that we need to know about the first derivative for now. If you want, we could go back to our function and say the minimum is going to be -3/2, comma, f of -3/2, and figure out what that's going to be. I'll let you do that later. We'll plot it all eventually. First derivative, check. We got all the information that we might need. This looks like it's a mess, but we'll organize it later. Now we want to move on to the second derivative and analyze things. So again, we're going to look for partition numbers of the second derivative. Instead of calling them critical numbers, though, because critical numbers only applies to the definition that refers to the first derivative, we're just going to check and see which ones are in the domain. It's really the same thing, but these ones don't have a name for the second derivative. And then we'll check all the concavity stuff. So we need the second derivative. Go ahead, try out some differentiation rules again, see what you can find, and see if you can get the second derivative. Pause the video, and then we'll pick it back up in a second. All right, this is what you should look like. Again, I went and pulled out a factor here, so when we're looking at partition numbers of the second derivative, it becomes pretty easy again. Here, x equals 0 is another partition number, but warning bells are going off saying, hey, that's not in the domain of f, so that's not going to be an inflection point. It's still a vertical asymptote, so we'll keep an eye on that. And we've got one more right here. That's going to be -9/2. Cool. And the only one that's in the domain is this one, -9/2. So this one is possibly an inflection point. We still have to check to see if the concavity changes here, but this one does have a possibility of being an inflection point. So we'll build our sign chart again. We should be getting pretty good at this. And I'm going to maybe put my little warning here again that says, hey, by the way, vertical asymptote. Nothing interesting other than that vertical asymptote going on here. Some people will go ahead and put that dotted line all the way through. Do whatever you need to, but remind yourself that you've got an asymptote. Let's check out the second derivative. Now, we're going to pick a number that is pretty negative, and we're going to plug it into this thing. So maybe let's pick like -5, because that's less than -9/2. If we pick -5, we end up with 8 times -5. That's going to be -40 plus 18. That's going to be negative. But when you put -5 into the denominator, that's going to end up being positive. So this is negative. Oops. There we go. That means for our function, it's concave down here. All right, let's check like -1, and we'll see what happens. If you put -1 into this, we get -8 plus 18. That is +10 over a positive, because -1 to the 4th is positive. Positive. Concave up. Meaning this -9/2 is an inflection point. So x equals -9/2 is going to represent an inflection point. And this vertical asymptote is happening here still, so this is not going to be an inflection point, even if the concavity changes, which maybe it will, maybe it won't. Let's take a look. Let's plug 1 in here. If you plug 1 in here, you're going to get a positive over a positive, and that means it's positive. That means it's concave up again. So both of these are concave up. Interesting. All right, we've got all the information that we might need. What we need to do now is sketch the graph. So I've got our axes here. Let's just start plotting some stuff. So I'm going to go all the way back to the beginning, and I'm going to check out where our asymptotes were. We've got a horizontal and vertical asymptote at 0 and an x-intercept at -3/4. So let's go ahead and put that stuff in here. I'm going to put my horizontal asymptote in. I'll draw it in red. Oh, that's my vertical one. Oh, no. That's diagonal. I'm really bad at drawing these, even with the straight line tool. Oh, well. There and there. And then I had an x-intercept at -3/4. Let's do these in terms of like ones and stuff like that here. Sorry, halves. So let's say that that's 1, that's -2, that's -3, -4, and -5. So there. So -3/4 is right here, right in between -0.5 and -1. Cool. Let me go ahead and actually, I want to erase these little things. Sorry, let me clean this up a bit. I don't need those tick marks on here. Oh, I dropped my asymptote. Let's put that back in there. So I'm going to go ahead and put in my 5, -5, -5. So that means my x-intercept is right there. All right, that's all the stuff we need from the function. Let's go check out the first derivative. We know we're going to have a local minimum at -3/2. That's -1.5. So our function, maybe I'll write this here. Our function is 4x plus 3 over x squared. So if we want to find f of -3/2, we've got to find 4 times -3/2, that's -12 over 2. That's -6 plus 3 over 9/4. So that's going to be -24. Well, -6 plus 3 is -3 over 9/4. That's going to be -12 over 9. And that's going to be -4/3. All right, so that's the y value that goes with the x value of -3/2. So -1.5 here, and then I'm going to go down a little bit over 1, about 1 1/3. So maybe we'll say like right around there. Now, I also know by the way that I found that we had this derivative that was equal to 0 here. That means we have a horizontal tangent line. So maybe I'll just plot that in there as well. Actually, you know what? I'm going to put it in blue. I also know that my graph is going to decrease and then increase. Then, after my asymptote, I'm going to decrease again. So we'll keep that in mind. All right, now let's take a look at the second derivative stuff. What did we have? We had an inflection point at -9/2, so we're going to need the y value for that. F of -9/2 is going to be 4 times -9/2. That's going to be -18 plus 3 over 81/4. -18 plus 3 is -15. -15 times 4 is -60/81. I don't really know what that is, but it's pretty close to -0.75. It's a little bit less than that, so that's where I'll plot it approximately. -9/2, that's -2.5. So there's 1, 2.5. And negative approximately 3/4, that's right around here. That is my inflection point. Now that means I know that my function is going to be decreasing, but it's going to start concave down. So now I can start sketching things. I've got this horizontal asymptote, so I'm going to start close to this. I'm going to be decreasing and concave down. Then if you remember, I'm still going to be decreasing, but I'm going to switch to concave up. And I'm going to level out flat with this because of my horizontal tangent line. Then I'm going to stay concave up, because if you remember, I go concave up to the vertical asymptote. So I'm going to stay concave up and increasing through my x-intercept, and then I'm going to go up really close. Oh, that's not very good. Let me try and fix that. Through my x-intercept, very close to this vertical asymptote, up that way forever. Now, I also know that I'm going to be decreasing again, because my first derivative said I was decreasing after the asymptote, and I'm going to be concave up, and I have to follow these asymptotes. So I'm going to look something like this. Decreasing, concave up. So that's probably what this graph looks like. And we've got an inflection point here at negative 9/2, comma 60 over 81. We've got a local minimum here at negative 3/2, comma negative 4/3. We've got an x-intercept here at, what was that, negative 3/4. And our asymptotes going on. The asymptote here was at x equals 0, and this one was at y equals 0. So lots of information that we can use to get this sketch, but realistically, I care more about getting the information together. Every now and then what we might do is just give you a sign chart, and you can kind of draw a sketch of what it looks like, or maybe match up a sign chart and a sketch of a graph, or maybe I could give you a picture of a graph and you have to tell me some features and tell me how to fill in a sign chart based on it, all that kind of stuff. But really, we're just trying to make a connection graphically between what's going on the function with what we're finding on that sign chart. Let me fix that horizontal tangent line there. Anyways, hopefully that's informative. There's lots of different examples that you can look at, but eventually you're really just going to be doing the same kind of thing. You're going to be analyzing the function by looking at x-intercepts, domain, asymptotes, all that kind of stuff. You'll look at the first derivative, try and figure out where it's increasing, decreasing, concave up, concave down, increasing, decreasing, find the local maximums and local minimums, And with the second derivative, you'll look at where it's concave up, concave down, and find inflection points. It's really kind of putting everything together. So it's a little bit tricky because these problems typically are long because we're looking at everything. So I'll try and split some of them up, but jump into there and see if you can get some pretty good pictures of graphs. Feel free to look at the picture of a graph on your calculator, but make sure that you can find all the features by hand. Good luck.